So here we're going to have a look at this in action. We're going to graph a cubic curve, and we're going to graph its first and second derivatives straight underneath, lining up the x values so that we can actually see how each derivative describes the gradient of the one before. Now in this form it's nice and easy to differentiate, so I might keep it expanded out like this for differentiation purposes. But when it comes to graphing this, I'm going to be finding it much easier if I prepare it by factorising it. So there's a few steps to think through here. Let's do the differentiations first and see what each derivative looks like. So here, if I differentiate one term at a time, I get 3x squared minus 12x plus 9. And if I then differentiate that, I'm going to get 6x minus 12. Alright, I think I can graph this one quite easily. That's got a y-intercept of minus 12 and a gradient of 6, so that's quite steep. When it comes to graphing this one and this one though, I feel like it would help me if I factorise them first so that I can see where the zeros or x-intercepts are going to lie. So with this first one, let's just prepare it by bringing an x out the front and then factorising the rest, and we're going to get this. And now that I've got it in that form, I can spot that I've got a perfect square here with x minus 3 times another x minus 3, or I can just put a square to show that it's multiplied by itself. So that's my cubic curve now. So if I want to graph that one, it makes sense. Well, let's actually make that go over a little bit further so you can see it better. Let's graph it just in the positive area. If I let y equal 0, x would have to be 0 or 3. Now, this is what's known as a double root. We've seen these before in year 11, but you might have forgotten about them. This means that it's not just any old x-intercept. It's got a squared on it. And a squared's a bit like a parabola, isn't it? Which reminds me that it doesn't go through the x-axis here, it just touches it and glances off. So I've got an x-intercept at 0, and then I've got one of these special double roots at 3. Now it's a cubic curve, so it's got that basic shape of going up, going down again, and then going up. So it must come up something like this, come down, and then go up again. That's a little bit dodgy, perhaps we'll make it shape more like that. There we go. Now that's, for our purposes here, good enough so that we can see the basic shape, and I can label that as x equals 3. Okay, now to graph the second derivative straight underneath, so here, this is y, and this is x. It's our original function. But underneath it, I want to graph y dash, and with still x here. And I'm going to make sure I've got the same scale on my x-axis so that I can see where everything's happening. Now, if I graph this one, I might need to prepare it a little bit first, so let's just do another line of working. I can bring a 3 out the front, can't I? And that gives me x squared minus 4x plus 3. And then I can factorise that even further, and I can see it's minus 1 and minus 3. So that tells me that when y dash equals 0, or in other words, when I want to find the x-intercepts of this thing, x needs to be 1 or 3. So that's here or here. And it looks like a parabola, doesn't it? And it's an upright parabola. So that's enough information for me to sketch in something roughly right like that. Now when I go to graph, well, I'm going to need actually a bit more space. I've sort of run out of board. I might need to use a slightly different scale on my y-axis, but I can use the same axis scale on my x-axis. Here I've got y double dash on the y-axis, and I'm graphing y double dash equals 6x minus 12. So it's got an intercept way down at minus 12, and if I want to find where the x-intercept is, let y double dash equal 0. So 6x would have to equal 12, x would equal 2. So that means it goes through here at 2, and I've lined up the 2 with the others, and it's going right down here. I don't quite have enough space for minus 12, so I might just make my scale a little bit different on both axes so that I can show generally what's happening. And I know that this is a straight line. Okay, now for the analysis, and this is the part where everything should start to make a little bit more sense. Obviously we knew how to graph all 3 of these things, and we can go ahead and graph them. But even if we didn't know how to graph these functions, and I just drawn a rough squiggle here, not knowing any of the exact points, we can take an original graph and build these 2 functions just by eye. Let's have a look at how to do it. Well, we said that this graph should describe the gradient of the one above. So let's look at the gradient of the one above and just describe it in rough terms and see if this is doing a good job of making that description. Well, the gradient looks to me like it's 0 here and here. These are two special spots on the curve where we've got gradient 0 there and 0 there. So if we look at when that happens in terms of x values, looks like that's happening around about x equals 1, and we can see it happens right on x equals 3. And sure enough, down here, this graph is graphing the gradient of this function, and it's saying the gradient 0 at x is 1 and x is 3. And sure enough, that's describing it perfectly. All right, well, what's the gradient on this side of this flat spot? Well, it's positive, isn't it? Okay, so what's the gradient on over here? Isn't that a negative gradient going down, you're thinking? Well, no, actually, this is just showing what the gradient is. So if there's a high level up here, and it's graphed on any of these points that are above 0, that's telling you that y dash is actually positive. So this positive gradient in this section of the curve is represented by this graph being above the x-axis. It's saying, yep, we've got positive values here. They're going down, but they're positive values. Why are they going down? Well, I guess this gradient is actually approaching 0. And so is this one showing the same thing. We've got a positive gradient, but it's going down towards 0. It's going to keep on going below. All right, well, what happens between x equals 1 and x equals 3? The gradient is negative for all of that time. It starts off 0, and then it becomes a little bit negative, and then it gets a lot more negative, and then it starts to get slightly bigger again and comes back to being 0 by the time we're at x equals 3. Let's have a look down here. Yep, that matches the description. It gets more and more negative until it starts to turn around and become more positive, and then it comes back towards 0 again. Okay, what happens from x equals 3 onwards? Well, the gradient's positive from there on. It starts off as maybe a very small fraction, and then it becomes bigger and bigger and bigger numbers. Okay, let's look at this graph. Yeah, it starts as 0, and it becomes small numbers in the beginning, reflected by these numbers down here, small positive numbers, and the numbers get bigger and bigger and bigger. Now, the other thing you might notice is that a cubic graph that has the highest power of x being x cubed will have a parabola as its first derivative. And that makes sense because when you bring that 3 down the front when you're differentiating, the highest power of x in the derivative will be x squared. And similarly, when we differentiate something with x squared in it, the highest power of x is just x itself. And that makes the derivative of a parabola a straight line. Now, let's examine whether or not this straight line accurately describes the gradient of this graph. Well, let's just think what the gradient of this graph is. It's negative, 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 until then it's 0, and then it becomes positive, 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 positive. Okay, well, down here, negative, 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 all the way till it gets to be 0, and then positive, 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 and keeps on increasing. So yes, this straight line does actually describe the change in gradient of this curve. And this parabola does describe the change in gradient of this curve. Now, we also mentioned that concavity is a key feature of a curve that we can analyse. Well, if we looked at the concavity of our original function, we would say, all right, this is concave down for this whole section here until it gets to here, and then from here on, it becomes concave up. Can you see that this is where it changes? Now, this is a special point. This is a point of inflection. We've seen them before, and we'll see plenty of them again. They can be horizontal sometimes, like if they're going along and then they go horizontal and then up. But this one isn't horizontal. It sits at an angle, if you like. But you can pick a point of inflection because it's where the concavity changes. And if you're using your pen to show what the gradient of the curve is at any one point, what you'll notice is that as you come along a section that has one type of concavity, you'll see that my pen is actually turning like a little circle here as I move it along. It's literally turning clockwise, isn't it? Well, when I get to the point of inflection, if I follow the curve, it actually starts turning the other way and starts turning anti-clockwise. And that's a dead giveaway that you've passed a point of inflection. Now, that tells us that the concavity is changing there. And so we've learnt that concavity that's positive is something that looks like this. It's a little bit like a cup or a smiley face. And positive concave up is where the second derivative is actually positive. Now let's see if that's true. Well, it starts from about here where x is 2, doesn't it? And sure enough, if we look down at our graph of our second derivative, that's exactly where it went from negative to positive, which is no coincidence. So this whole section of the graph is concave down. And that means, if it's concave down, that the second derivative is negative there. It looks a bit like a frowny face, and that's one way that I remember. Frowny face, second derivative is negative. And sure enough, negative all the way along here, but from there on, we have the shape of a smiley face, so the second derivative is positive, and sure enough, from there on, it's into positive numbers.